Today, we want to talk about some more trigonometric identities. Remember, these are not things that you need to memorize. They're just things that you need to remember. If you remember things by sitting down and memorizing them, then that might be one way to go. More importantly is to remember that these types of things, these formulas, these identities have categories and names. Remembering that these categories exist is probably the most important thing moving forward. So that later on, when you're in your calculus classes and you start seeing trig functions and you get stuck on a problem, you immediately need to think there's probably an identity that will get me out of this stuck situation. For the most part, if there are trig functions around and you are stuck on a problem, you need to find an identity that might help you. There's probably an identity running around waiting for you to get waiting for you to find. So you got to remember the categories of trig identity that exist so that you even have a chance to look them up. If you have no idea that trig identities of this form even exist, then you don't have a chance to look them up. But if you remember that they exist, it's like, well, isn't there an identity for that? And you can remember a little bit of the form, then you can look up what that identity is to see if it will help you. Does that make sense? A lot of times we're too quick to decide that we could just look stuff up later. If you have never been exposed to the thing that you're supposedly going to look up later, if you don't remember that such a thing exists, then being able to look it up later doesn't matter. If it's not even something you'll ever think to look up. So it doesn't help to be able to look things up later if you need a sum and difference identity, if you need the cosine of a plus b, and you don't even remember that the cosine of a plus b is a thing. Does that make sense? Here's the good news. There are a ton of trig identities. And once we see them all, we can see how they are connected to these identities. And so learning the ones that come from the sum and difference identities will help us remember the sum and difference identities, and it'll help us remember the double angle identities. It'll help us remember the half angle identities. We get to know all these extra things once we see them all, once we get the big picture. Instead of picking it a piece at a time, it's best to have it all at once. And this is where we can start. This is where I like to start. So let's talk about sum and difference identities. This is when we have a cosine or a sine of a sum or a difference. So you can see that right there. Sum is plus, difference is minus, and I want to apply cosine and sine to plus and minus. The main reason that I want to do this is that there's parentheses. It's cosine, parentheses, a plus b, close parentheses. And because of the way we teach the distributive property, people be like cosine a plus cosine b, because you just distribute stuff. But cosine is not being multiplied by the sum of a plus b. Cosine is a function that's being applied to a plus b. It's cosine of a plus b, not cosine times a plus b. So the distributive property doesn't apply just because we see parentheses. Does that make sense? If there is one thing you walk out of this classroom with at the end, besides the passing grade, is that parentheses don't mean distributive property. If I sound mad when I talk about the distributive property, I am, because of what happens. Cosine of a plus b, I know how to deal with parentheses. It's the first one in PEMDAS. It's not an operation. Fuck's sake, it's not an operation. Order of operations, first thing listed, P. For the one that's not an operation. I'm just kidding. I'm not really that mad about it. All right, so let's take a look at some things. So we've got cosine of a plus b is cosine a cosine b minus sine a sine b. Cosine of a minus b, cosine a cosine b plus sine a sine b. More important than the similarities is the differences. What happens when we change things up to sine? Sine of a plus b is sine a cosine b, cosine a sine b. This is the one that I chose. I chose to write the one from the book. I don't know why I hate this so much. I hate this so much. Because the other way to write this one, your alternative is to say sine of A plus B is to be sine A cosine B plus sine B cosine A. So I don't like sine, cosine, cosine, sine. I like ABBA style, ABBA. So I definitely prefer ABBA style to switching up the trig functions. So I would write sine of A minus B as in ABBA style, sine A cosine B minus sine B cosine A. All I'm doing is switching the order of the multiplication in the second term. So this is ABBA style. But it makes sense. I can see what they were going for. This is more of an AB style. And so they were just mimicking AB style. I don't like the AB style for both. I like AB style for cosine, but I like ABBA style for sine. Both because I can get away with it. And now in the back of my mind, I'm doing the class 2 dancing queen. I mean, that's just much better. Or it could be that I write both of them down so that we get to say them more often and you get to write them more often. That's called an ulterior motive. And that's very manipulative on my part. I'm not sorry for being manipulative. So check out the big difference between the cosine and the sine. There are two major differences. Cosine is the one where they're the same. Cosine, cosine, sine, sine. That's what the term structure is. The cosine has cosine, cosine, sine, sine. The difference when we go to sine is it's sine, cosine. Sine, cosine, cosine, sine, or sine, cosine, sine, cosine. So the sine has the mixed ones. Cosine has the same trig functions. Everybody see that? Cosine is the cosine, cosine, sine, sine. Sine is the mixed. But check out what happens. The cosine of A plus B, the sign in between the terms is minus. The cosine of A minus B, the sign in between the terms is plus. So the cosine one uses the cosine. Plus, minus, or inverse is not cosines, but it's different. With the sine, sine of A plus B, the sign in between, plus. Sine of A minus B, minus. So the sine sum and difference identities matches the sign. S-I-G-N, not S-I-N. Cosine and sine. Very strange examples when you're reading along in the book. You see, oh, this will be useful for finding the exact value of, let's say, I wanted to find the sine of 15 degrees. Now, 15 degrees is not one of the ones that we know. 30, 45, 60, 90. Multiples of 30, multiples of 45, multiples of 60, multiples of 90. Those are the ones we know. We know that those going all the way around the unit circle. 15 is not one of them. But 15 can be made with two of them. I can think of the 15 as being 45 and a 30. So we could think of sine of 15 as the sine of 45 minus 30. So we can write the thing that we don't know in terms of things that we do know. I know sine and cosine of 45 and 30. So I can use my difference angle identity for sine and say this is the sine of 45 times the cosine of 30 minus the sine of 30 times the cosine of 45. Those four values are ones that we do know. So sine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Sine of 30 is a half. Cosine of 45 is root 2 over 2. So we get root 6 over 2 minus root 2 over 2. No, we can't. Exponents, the square root of 6 and the square root of 2, those are both exponents of 1/2, and exponents do not distribute over sums. Oh, because I got a square root of 2 times the square root of 3. Exponents do distribute over products. So square root of 2 times the square root of 3, we can write as the square root of 6. Oh, it's not 2 in the denominator, it's a 4. 2 times 2 is not 2, right? These are 4s as well. I'll just make them fancy 4s. Or bold 4s. Square root of 2 times the square root of 3 is the square root of 6 because exponents distribute over products. But the square root of 6 minus the square root of 2 is not the square root of 4 because exponents do not distribute over sum. I've got a 6 to the 1/2 power minus 2 to the 1/2 power. I can't write that as 6 minus 2 all to the 1/2 power. Exponents don't distribute over sums. Yeah. Well, we need a trig function for a half of an angle. That's one of the identities that we'll learn, a half angle identity. But the sine of 15 is not half of the sine of 30. Otherwise, this would have been just a fourth. Because once again, sine, we can't just distribute the sine to a 30 and a 2. Always be careful if you get the last cup of coffee out of the food. Because the last cup of coffee in the machine is chunky style coffee. So some of the cool stuff that's going on here. Square root of 2 times the square root of 3 is the square root of 6. Exponents distribute over products, not exponents. So remember, the square root of 2 is a 2 to the 1/2 power. And if I multiply that by 3 to the 1/2 power, I can write that as 2 times 3 all to the 1/2 power. Or 6 to the 1/2 power. But over here, square root of 6 minus the square root of 2, exponents do not distribute over sums. Also, we have sine of 15. The other question came up is sine of 15. We could write 15 as 30 divided by 2, but that doesn't help us. So the sine of 15 is equal to the sine of 30 divided by 2, but this 1/2 is inside the sine. 30 gets divided by 2 first, then we apply the sine to it. There's no way to get that 1/2 out of that sine. That 1/2 is stuck in there. So we need a way, we needed some other way to deal with that 30 over 2. There is an answer to this, but it's not as simple as just pulling the 1/2 out. Because that 1/2 is inside, the 30 gets divided by 2, then we take the sine. I can't switch the order on this. Because the trig functions do not distribute over products. So I wouldn't be able to do the sine of 30 divided by the sine of 2. I can't just distribute things like that. So here's one category of trig function. This is the one that the other ones are going to be based on. So we take our sum identities. If I make A and B the same in our sum identities, we get the category called the double angle identities. Let's just make a new page. A and B are just any two angles. Yeah. Oh, that's a good question. Yeah, it could just be like we're adding or subtracting two angles like we did with this 45 and the 30. But we could also imagine angles on the unit circle. Say an angle A. And then an angle B. Where B starts here at the end of A. There's an angle B. And then this angle that's the angle A plus B. So we're getting a relationship between the points here at the end of A, here at the end of A plus B. And if we had moved B back, rotate that through A. So in this drawing, the B starts at the A, so I can see the whole angle A plus B. So the next, another category are double angle identities. This is just going to make A and equal B in the sum identities. So this is not new. This is just a modification of the old ones. So we're just going to take the sum identity and make A equal to B. We're also going to get the opportunity to remember our sum identities. Cosine of A plus B, Cosine is the one where it's matchy-matchy, but different sign. So if I make A equal to B, I can write cosine of A plus B as cosine of A plus A, or cosine of 2A. That's going to be the cosine of A times the cosine of A minus the sine of A times the sine of A, or cosine squared A minus sine squared A. Remembering this double angle identity will help us remember the sum and difference identity for cosine. Because if we remember that cosine of 2A is the cosine squared A minus sine squared A, this cosine squared happened because there's a cosine cosine, and the sine squared happened because it's sine sine. And it's minus, so even though it's plus, for cosine in the sum, cosine of A plus A, it's cosine A minus sine A. So that helps reinforce remembering our sum identity for cosine. No, I just took the first identity, cosine A plus B, and I replaced B with A. Oh. Just to make a double angle identity, I just make the two terms the same. A plus A is equal to 2A. Here's the double angle to which we're referring. As A plus A is equal to 2A. That's the double angle part. So we're going to remember cosine of 2A is cosine squared A minus sine squared A. We don't have to memorize this, we just have to remember it. Our memory of this is reinforced by remembering our sum identity for cosine. Our sum identity for cosine reinforces our memory of the double angle identity for cosine. Your double angle identity for cosine is a cosine squared minus sine squared. So this has a lot of Pythagorean identity overtones, right? Because sine squared A plus cosine squared A is equal to 1. That's how Pythagorean is. What this means is that since this double angle identity for cosine involves cosine squared and sine squared, I can replace sine squared with 1 minus cosine squared. So I can write the cosine of 2A as cosine squared A minus sine squared and so this becomes cosine squared A minus a minus is plus, so 2 cosine squared A minus 1. So there's a variation on our double angle identity for cosine. You don't have to memorize it, you do have to remember it though. Later on, when you're in Calc 2, this one's going to be super important. I normally have great amounts of disdain for it. This is going to be important later on, but this one is going to be important later on. So like when you show up in my Calc 2 class, Michael, What are we going to do with this stupid cosine? It's causing us all these problems. It's cosine squared. You're going to be like, well, can we use a double angle identity? I'm like, oh, son of a bitch. You actually remember that? So this one. We love this one so much. Because I can't leave things alone, I just replace the sine with 1 minus cosine squared, sine squared with 1 minus cosine squared. You might be thinking, what about replacing cosine squared with 1 minus sine squared? And I'd be like, oh, heck yes, I'm going to do that. But not in orange, it's going to be in blue. Because I can rewrite this identity as with cosine squared A. I can write that as 1 minus sine squared A. So I can replace this cosine squared A with 1 minus sine squared A minus another sine squared A. Oops. And I can end up with 1 minus 2 sine squared A. That one is cool, but not nearly as cool as cosine of 2A. 2 cosine squared A. Remember the 3 important tricks of mathematics. Add 0, multiply by 1, change your variable. Knowing your trig identities helps you change your variable. Helps transform one problem into a different problem that might be easier to solve. Knowing more is always better. One thing to notice here is that this side of the identity involves sine squared. It's an exponent. Exponents we know can cause some problems. The exponents don't distribute over sums and things like that. Sometimes it's more convenient to have multiplication. If we can get rid of an exponent and drop things down to a multiplication, then sometimes we're better off. Now, this is a double angle identity for cosine of 2A, but there's also one for sine of 2A. Remember, the sine of A plus B is the sine of A cosine of B, because it's the mixed one. Cosine is the same trig function, so sine is the mixed one. And sine also keeps the same sign. I'll do AB style since that's what the book does. You might be reading along in the book. But we're going to do the same thing. We're doing a double angle identity, so I'm going to replace the A with or replace the B with an A. So I'm going to write sine of A plus A. That's going to be the sine of 2A. So it's going to be sine A cosine A plus cosine A sine A. And we notice that one of them is sine A, cosine A. The second term is cosine A, sine A. I've got 2 copies of the same thing. So I can write the sine of 2A is 2 times sine A cosine A. Here's the double angle identity for sine. Knowing this reinforces our memory of the sum identity for sine. The sum identity for sine is the mixed trig function one. The sine and cosine are in the same term. Whereas the cosine sum and difference identity, that's the one where we use the same trig function. Cosine, cosine, sine, sine. Versus cosine, sine, cosine, cosine. ABBA style, it works out the same way. I'd write sine A cosine B plus sine B cosine A. And then when we make them all the same, I'd have sine A cosine A plus sine A cosine A. And it's still 2 sine A cosine A. Is everybody okay? You don't have to memorize these, you just have to remember them. The first step in remembering them is remembering that they exist. Remember that they are a thing. Once we remember they are a thing, we can start to build some judgment about whether it's better to have a multiple of the argument or a power of our trig function. Yes. If we're trying to solve an equation that has an even exponent in it, that's going to tend to lead to 2 solutions. Multiplication will not. Say again? Correct. But if we're going to get rid of being multiplied by 2, we just have to divide by 2. All right, let's take a break. Come back and turn our double angle identities into half angle identities.